Hello, juniors. Today we're going to continue with the topic about exponents, and specifically we're going to be talking about the exponential function today. We have seen the different laws of exponents, then we have seen how to solve exponential equations, and now we're going to get into the analysis of the exponential function itself. Okay, so the objectives for today's class are identify exponential functions and their graphs, solve exponential equations, understand the different types of transformation of graphs, apply composite transformations. So this part about transformation is also a review from the topic we've seen in the first term, right? The different types of transformations. If you remember, translation, reflection, and stretch or compress are the different types of transformations we've seen. Okay, so first let's define what an exponential function is about. It's a function in which the dependent variable y increases or decreases exponentially with the independent variable x. Okay, so that's the typical curve that has this shape. Let me show you. This one in which we increase exponentially is the exponential function. Okay. So, some real-life applications of exponential functions. First of all, this one. How can you model the sales of smartphones between 2003 and now? Can this model be used indefinitely? So, definitely the sale of smartphones has been having an exponential growth ever since 2003. But maybe we're in a time in which that exponential growth isn't as big as it was before, right? When having a smartphone was a boom, probably. Okay. Another example: earthquakes can be measured in the Richter scale. Sound is measured using a decibel scale. What do these two scales have in common? Why is this scale more convenient to use? Okay, so for this particular scale, the Richter scale, and I believe that for the decibel scale also, we're talking about logarithmic functions in order to calculate this, and the logarithmic function is also kind of an exponential function. We're going to see the relationship between those two functions later on, but basically the logarithmic function is the inverse function of an exponential function. Okay, in the last example here, it says, what model can you use to find the temperature of a cup of coffee at any instant as it cools down? Right? When you put your coffee in a microwave and you take it out, it starts to cool down until it reaches room temperature, right? You may have studied this in physics already, but you know that any object that has a temperature higher than the room temperature will decrease its temperature, but only up to the room temperature, unless some type of energy is inserted to the object, which makes it cool more than room temperature or get hotter more than the room temperature, right? So if we take up a cup of coffee from the microwave and it starts to cool down until the room temperature, the model, or if we have a graph of, let's say, time and degrees Celsius, right? The model will be maybe something like this, right? It's going to be decreasing. This is known as an exponential decay, okay? We're going to take it out from the microwave, let's say at 80 degrees Celsius, and then it's going to be cooling down, but the rate at which cools down decreases as time goes by, right? And the room temperature is let's say 24 degrees. The room temperature is an asymptote in this case, okay? So this is a very interesting topic for if you want to think about a math project idea for next year. Let me write this down. This is a good internal assessment, which is the same as saying project topic, okay? So for you to start thinking about. Okay, other examples about exponential applications. For example, population growth. You know that the population increases exponentially, especially if we're talking about For example, bacteria, when you study that in biology, how bacteria reproduces, simulates an exponential function, right? Another example, this is very contemporary, right? COVID-19 confirmed cases. If you look at the graphs for the confirmed cases, you will see that it has an exponential increase, right? It started slowly during the first days of January, February, and then it started to increase exponentially. And another example is compound interest, right? Whenever you are depositing money, for example, in a bank, the bank sometimes offers compound interest for your savings. And that means that the more time you leave your money there, the more interest you're going to generate. And that means that you're going to be having more money in the future, right? We can dedicate a whole class about this topic later on, okay? But that also models an exponential function. Okay, so let's move on to this investigation in order to see more about exponential functions. It says, the bacterium streptococcal pharyngitis can double its number in 30 minutes. At 9 a.m., there are 1,000 bacteria cells in a sample. So it doubles every 30 minutes. So copy and complete the table showing the number of bacteria cells present at each time, right? So here we have a time, first of all, and we have every half an hour. We're going to be analyzing every half an hour. And thousands of cells, right? For 9 a.m. it says 1. That means that we have 1,000 of cells, right? As we are given the data at the beginning, right? So if this population doubles every 30 minutes, that means that at 9:30 a.m. I should have 2,000 of cells, right? Then for 10 a.m. I would have double of whatever I have at 9:30 a.m. Sorry. So 2 times 2, we double that 2 and we get 4. So at 10 a.m. we already have 4,000 cells. Then at 10:30, once again, we double this value and we get 8. So then at 11 a.m. I would have 16. 11:30 I would have 32. And finally for 12 p.m., 32 times 2, that's 64,000 cells. So imagine, I started at 9 a.m. with only 1,000 cells, and 3 hours later I have 64,000 of cells. That's 64 times greater than what I had 3 hours before, right? That's how exponential functions work, basically. Okay, so here's a TOK question. It says, the phrase exponential growth is used popularly to describe a number of phenomena. Do you think that using mathematical language can distort understanding? So that's just for you to think a little bit about. Okay, number 2. How many bacteria cells will there be at 12 p.m.? So now we know that at 12 p.m. we're going to have 64,000 of cells. Thousands of cells. Okay, then it says for number 3, use graph paper to plot a graph of the number of bacteria cells in the sample from 9 a.m. to 12 p.m. You should let 9 a.m. be 0 on the x-axis, 9:30 be 1 on the x-axis, and so on. Join up the points to sketch a smooth curve. Okay, so to buy some time, I have already made the axis, right? You see that my x-axis begins at 9 because that's what the problem tells me, and then we go 9:30, 10, 10:30, and so on. I decided to use 3 squares for each unit just to make this graph more clear, okay? And for the y-axis, which is 1,000 of cells, so the x-axis is time, the y-axis is 1,000 of cells, I went up to 65 because I know that the maximum amount I would get for 12 p.m. is 64. So I did my graph going 5 to 5 until I got to 65. Okay, so I'm going to plot the points we just calculated here. Let me see. For 9 a.m. we have 1, so I'm going to plot 1 should be somewhere around here. Then for 9:30 we have 2, 9:32, that would be a little bit more above the other. Then we have 10 a.m. 4, so 10 a.m. 4, that's somewhere around here. 10:30, we should have 8. 10:30, we have 8, that's already around here. Then for 11, I have 16, right? Doubles the 8, so that's somewhere around here. Then for 11:30, I should have 32. 32 is somewhere around here. And finally, for 12, I would have 64, which is somewhere around here. So you see how if I join this point, it says join up the points to sketch a smooth curve. Whenever we need to join this point, you see that this is not a straight line. So I need to join by hand, okay, without using a ruler. So if I do that, you would see a perfect exponential function, right? Let me do this in 2 steps. There you go. So you see that this is an exponential function. The population increases exponentially as time goes by. Okay. Number 4. By drawing the line y equals 50 on the same set of axes and finding the x value at the point where the line intersects the curve, find the time when there are 50,000 cells. Okay, so if I draw the line y equals 50, I am going to be finding at what time we have 50,000 cells, right? So if I draw that line y equals 50, let me do that with green. Y equals 50 is right here. This is 50. So the line would be this one over here, and it intersects the graph right there, right? If I take this down to see where it intersects the x-axis, it's somewhere around there, right? Let me take this out here, and this would be, it's hard to tell. This is half, this is, sorry. So this is half, this is the other half. So it's somewhere around, I would say, 45, 1150 maybe, right? No, 1145. Yeah, let's say it's 1150. Okay, so by 1150, this population should be around 50,000 cells. Okay, so that's how we can solve this using our graph. Then for number 6, I don't know why it skipped number 5. It says, what is exponential growth or decay? So if you look at this graph, this is a case of exponential growth, right? Let me write this here. Exponential growth. Because the population is growing as time goes by, right? But there might be other cases, such as, for example, the decreasing temperature when we take a cup of coffee from the microwave, in which we're going to call this exponential decay, okay? If it decreases exponentially as time goes by, we're talking about exponential decay. If it increases exponentially as time goes by, we're talking about exponential growth, okay? Perfect. Then we have number 7. It says, how do exponential functions model real-world problems and their solution? Okay, so that's just something to think about, right? We can use exponential models in order to make predictions about different types of real-life situations, right? Then it says, reflect. Find the meaning of exponential growth and decay and discuss your answer with a classmate about how this relates to your function. Okay, that's just for you to think. Then we have the mathematical definition, right? An exponential function is a function in the form f of x equals a to the power of x, where a is a number greater than 0 and a is different from 1. Why does it say that a should be different from 1? Because if you think about, if a is equal to 1, for example, 1 to the power of x, then independently of whichever value I pick for x, 1, 2, 3, 1 to the power of 2, 1 to the power of 5, 1 to the power of -1, and so on, 1 to the power of any number is always equal to 1, right? That's why in order to be an exponential function, the base should be a value different from 1. Okay? So basically, what you need to know is that an exponential function is a function that has the variable x in the exponent, right? Whenever you see the variable x in the exponent, you should automatically think about an exponential function. And pay attention with that because, for example, this function, let's say x squared plus 2x, this is not an exponential, not exponential. This is a quadratic function, right? Because we have the x squared here. So the rule is, in order to identify an exponential function, the x must be in the exponent, okay? If there's no x in the exponent, then we're not talking about an exponential function, basically. Okay, then we're gonna see this investigation. It's where we're gonna be analyzing how the exponential function changes when we apply different transformations, and we're gonna analyze the characteristics of exponential functions. It says, use your GDC to help you sketch on the same set of axes the graph of y equals 2 to the power of x, 3 to the power of x, and 4 to the power of x, okay? To buy some time, I have already put the answers for this. So for number 1, let's go, if we scroll down, you have the answers here. If we plot the three functions, look at the three functions. Y equals 4 to the power of x, 3 to the power of x, and 2 to the power of x. So you see that all of these are exponential functions, and what the different bases are causing are the change in steepness of these exponential functions, right? The greater the base, the more steep the function is, okay? But you see that, for example, they all share the same y-intercept, and also they all share the same horizontal asymptote. Okay, so that's something very important for you to consider. We're going to see that in the following questions. Number 2, for each of these functions, can you find the equation of the asymptote? If we look at the graph, you see that all of them have the same horizontal asymptote, which is y equals 0. Okay. Number 3, where do the functions cross the y-axis? Can you explain why this is the case? So you see that all of the three functions are crossing the y-axis at exactly the same point, right? And why is this true? How do we find the y-intercept? Let's do that here. To find the y-intercept, the condition is that x must be equal to 0, right? So if we do that with all of our functions, let's say the first one, y equals 2 to the power of x. If I replace the value of x with 0, I'm going to get 2 to the power of 0. And any number to the power of 0 is 1. Okay? So this is 1. And if I do the same for all of the other functions, you would see that I would always be getting 1 as my y-intercept. Okay? So it doesn't matter if the base is a different number. Any number to the power of 0 is always equal to 1. That's why they all share the same y-intercept, which is the point 0, 1, right? So it says all three intersect at y equals 1 because any base to the power of 0 is 1, basically. Let's go to number 4. What is the domain and range of each function? If you look at this graph, what will be the domain and the range of all of the functions? You see that for the domain, the x values, this function can take any number, right? This continues up to the infinity to the negative values, and this continues up to infinity, positive infinity, for the positive x values. And you see that for the range, this function only goes from 0 to infinity, right? So the range is only the positive numbers, basically. And that's true for the three functions. All of them have the same domain and range. So it says for all three, the domain is x belongs to all real numbers. That means from negative infinity to positive infinity. And y is greater than 0 is the range. Okay. Then we have number 5. It says, what effects does the value of the base have on the graph of the exponential function? And that's what I just explained, that it changes the steepness of the function, right? The greater the base, the more steep the function is. And here it says, for an exponential function, the value of the base determines the scale factor of the vertical stretch. Okay, that's a more decent way of explaining what I just said. Let's move on to number 6. It says, use your GDC to help you sketch the graphs of y equals 2 to the power of x plus 2 and y equals 2 to the power of x plus 2. Okay, so if you remember, what type of transformation is this? Whenever it's not affecting the x, we're talking about a vertical translation, right? In this case, it's 2 units up because it's positive 2. In this case, when the constant number added is affecting the x, we're talking about a horizontal translation. And since this is plus 2, remember that it's 2 units to the left. Okay, horizontal translation, 2 units to the left. So that's what we should be able to see in these graphs. Okay, so if you may sketch this in your calculators and you would see. So the red function y equals 2 to the power of x plus 2, you see that this function is displaced 2 units to the left, right? It has been moved 2 units to the left. And in this case, y equals 2 to the power of x plus 2, you see that this function shifted 2 units up. You see that instead of having the y-intercept at y equals 1, the new y-intercept is at y equals 3, okay? So that would change some things a little bit. Let's go to number 7. Number 7, describe the transformation that map the graph y equals 2 to the power of x onto each of the graph in question 6. Okay, so that's what we just said. Y equals 2 to the power of x is translated vertically up 2 units to map onto y equals 2 to the power of x plus 2. Okay, and y equals 2 to the power of x is translated horizontally 2 units left to map onto y equals 2 to the power of x plus 2. Okay. Then for part 7b, let me see. Yes, that's it for number 7. So for part 8, it says, use your GDC to help you sketch on the same axis the graphs of, and now we have these functions, y equals 2 to the power of negative x, y equals 3 to the power of negative x, and y equals 4 to the power of negative x. So what's the difference? In this case, we're having a negative exponent, okay? So we're going to see how the negative exponent acts on the graph of the function. If you remember from transformations, when we change the sign of the x, we're doing a reflection on the y-axis, right? The x values change signs, so we have a reflection on the x-axis. So if you do this in your calculator, you should get something like this, right? You see that we're getting exactly the same functions, but now they are translated in the y-axis, right? The originals were something like this, if you remember, like this. So they are reflections on the y-axis, okay? So once again, the number of the base, what changes is the steepness of the function. The greater the base, the more steep it would be. Okay, then we have number 9. How is the graph y equals a to the power of negative x the same as the graph of a to the power of x? Okay, so if we compare what we did here with what we're doing now here, what do they have in common? One thing they have in common is that they still have the same y-intercept at y equals 1, right? 0, 1. And also another thing they have in common is that they still have the same horizontal asymptote, which is y equals 0. Okay? And then another thing we can analyze is that the domain and range for these functions are the same as what we had in the previous case. Domain are all real numbers and the range are all positive numbers from 0 to infinity. Okay, so that's the answer for part 9. They have the same domain, range, y-intercept, and asymptote. That's what they still have the same. Then we have number 10. It says, how is the graph y equals a to the power of negative x different from the graph y equals a to the power of x? How are they different? Well, one is a reflection of the other in the y-axis, right? And we can say that this is a case of exponential decay, and this is a case of exponential growth. Those are the differences. Let's see. Y equals a to the power of negative x and y equals a to the power of x are reflections of one another in the x-axis. So I can add what I just said. Y equals a to the power of negative x is an exponential decay there, and y equals a to the power of x is an exponential growth. That's another difference. Finally, part 11, factual. If y equals 2 to the power of x is the parent function, copy and complete this table to summarize your findings about the parameters of an exponential function, okay? So here's a summary of what we just saw, right? If the parent function is 2 to the power of x, then y equals a times 2 to the power of x is a vertical stretch with a scale factor a. Y equals 2 to the power of a times x is a horizontal stretch with a scale factor of 1 over a. Y equals 2 to the power of x plus b is a vertical translation, b units up. Y equals 2 to the power of x plus c is a horizontal translation, c units left. Y equals 2 to the power of negative x is a reflection in the line x equals 0, that is the y-axis. And y equals negative 2 to the power of x is a reflection in the line y equals 0, which is the x-axis. Finally, question 12, how do the parameters of exponential functions affect the graph of the function? We have already discussed this. The parameters of the exponential function transform the function by altering the asymptotes, the range, the rate of growth or the decay, and its intercepts, okay? So that's all the different things that change whenever we change the parameters of the function. Okay, finally, here's a summary. It says characteristics of exponential growth. F of x equals a to the power of x. This is the function for exponential growth. And here's just a summary of what we just talked about, right? The domain of f of x is the set of all real numbers. The range is a set of all positive real numbers. The curve does not intercept the x-axis. The graph approaches closer and closer to the x-axis as the value of x decreases. That means that the horizontal asymptote is y equals 0. The y-intercept is 1. The graph of the function passes through negative 1, 1 over a, 0, 1, and 1 over a. The graph increases continually. And for exponential decay, this is a graph of exponential decay, right? F of x equals a to the power of negative x. And these are the characteristics. Domain are all set of real numbers. Range are all positive real numbers. The curve does not intercept the x-axis. So up to here, it's all the same as exponential growth. The graph approaches closer and closer to the x-axis as the x values increases. There's a difference here. The horizontal asymptote is still y equals 0. Then the y-intercept is 1, just as in exponential growth. The graph of f passes through these points, and the graph decreases continually, okay? So here we have a direct comparison between the two, right? In this case, the function has base e, okay? Which is something that we're going to be studying more in depth later on, okay? So for next class, we're going to be solving some examples about exponential functions, just to make this clear. But I think that if you understood this clearly, you shouldn't struggle much with the problems we're going to be seeing later on, okay? So I hope this was clear enough for you. If not, please let me know, and have a nice rest of the day. See you.